Welcome back. So now that we have described the main problem, let's say, of how to store data in the cloud, and we saw some, advantages and disadvantages of using the traditional encryption techniques, we are ready to move on to describe a kind of proper cryptographic cloud storage. So we said in the previous video that our main goal basically is to describe some promising modern cryptographic techniques, and one of them was symmetric searchable encryption. The other one was attribute-based encryption. So let's start with symmetric searchable encryption and see how it works and what it is basically, and how we can use it to the cloud to do, to store our data securely in the cloud and do certain operations on the encrypted data. So again, we've got Alice and Bob. So imagine that now Bob is basically the CSP, the cloud service provider. Alice is generating a file locally on her machine. So imagine that this file contains a bunch of data, keywords, and then she encrypts also locally a symmetric key, a symmetric encryption key. Now she uses that key to encrypt her file locally, and this generates basically a ciphertext that only Alice can decrypt, because she's the only one who has access to the corresponding encryption and decryption key, to the corresponding symmetric key. Right now, the idea of symmetric searchable encryption is that Alice will contact Bob and will send to Bob the encrypted version of her files. Right now, so Bob, the only thing that he can do with that file is store it in his local storage resource, because he doesn't have access to the symmetric key that was used by Alice to encrypt her data, right? So upon reception, the only thing that Bob will do is that we'll get that encrypted file and just store it in his local database, right? Now, the magical thing with symmetric searchable encryption is that Alice, she's able to basically send search queries to Bob by saying, okay, please return to me, find all the data, for example, that contain the work Tampere University, right? So upon reception of that query, Bob will be able to find all the data that he has stored in his local database and contain the words Tampere University, right? And return back those data to Alice, who upon reception, basically Alice decrypts the data locally with the symmetric key that she knows, and she can process the data and so on and so forth. Now, the important thing to mention here is that in that step where Alice is sending the query, the search query to Bob with the keywords Tampere University, Bob doesn't basically, in a proper SSE scheme, Bob should not be able to get access to the actual keywords that Alice is looking for. Nevertheless, he should be able to find all the files containing those keywords, right? So basically, we keep all of our most of our data encrypted, hidden from Bob, right? So Bob doesn't have any way to know the keywords that Alice is looking for. So, however, he can find all the files containing those keywords. This means that if Alice searched for the same keyword after a while, Bob wouldn't be able to realize that those two search queries were identical, right? They should be different. They should look different at Bob's side. That's how we protect, we provide a better security and privacy to Alice. Anyway, so this is the main idea of SSE, symmetric searchable encryption, right? So let's see a bit more details of how this works. So Alice generates her file locally. Let's say that that file contains a bunch of keywords like, for example, Asclepios, security, coronavirus, right? Then what is going on is that on client side, Alice, what she will do is that she will have a program that will generate, first of all, a symmetric encryption key, right? A symmetric key that will be used basically to encrypt this file. Before we encrypt this file, Alice needs to have on her machine a process where it will start parsing that file, okay, and extracting each keyword of that file, okay, and then hashing that keyword. So you start parsing. Alice's software starts parsing. Alice's client starts parsing the software, the file, finds the keyword Asclepios, generates the hash of Asclepios, and then moves to the next keyword, security. Generates the hash of the keyword security, and then moves to the next one, and so on and so forth until it ends the document, right? Now, after this phase finishes, basically Alice is using her symmetric key, her secret key, to encrypt the file, right, and generates an encrypted version of the file. So till now, what we've got here is that we've got a list of hashes of the keywords contained in the file, as well as an encrypted version of the actual file, right? Good. So what will Alice then send to Bob is she will send. I try to simplify things first of all, right? But anyway, it just you need to get the main idea here. So she will send two things: the encrypted version of the file, okay, which is encrypted with the secret key that Alice has generated and has never shared with Bob, right? So Bob cannot decrypt that file, and a list of all keywords, the hashes of all words contained in that file. Again, since we know that a cryptographic hash function is not reversible, so Bob cannot basically reverse those hashes, which means that Bob cannot get access to the contents of the file, right? So he cannot tell that this hash corresponds to the word Asclepios, or that this hash corresponds to the word security, and so on and so forth. So all the contents of the Alice's data will remain hidden from Bob. Upon reception, what will Bob do is that he will store basically in his database a mapping of the keywords on the file, the ciphertext that these keywords can be found at, right? So the hashes of the keywords and a mapping with the encrypted file name that is stored in his local storage resource. Now, after this process has been finished, then basically Alice deletes her data from her local computer, right? So basically, she does not have this file anymore in his local computer, right? So all of her data has been encrypted and sent to the cloud, right? So no plain text data stands anywhere, and basically Alice does not need to have any kind of replicas of her data locally. Good. So let's see now how the search works. So we've got now another user, okay, that let's say wishes to get to search over Alice's data. So let's assume that Alice has somehow shared the secret key that was used to encrypt her data with that user. Now, in order to perform a search query, you need to search for a certain keyword, right? So basically, that user will contact Bob and will say, hey, Bob, please give me back all data that contain the word coronavirus. Now, the important thing to notice here is that instead of sending the keyword in plain text, like coronavirus in plain text, our friend here will send the hash of the keyword. Now, in most encryption schemes, most SSE schemes, this is not exactly how it works, because if you just do it like that, then Bob can breach your privacy, or anyway, any other malicious user can potentially breach your privacy. So things are a bit more complicated. We use the keyed hash function and some other tricks. But anyway, here I want you to get the main idea, right? So basically, instead of just sending the keyword in plain text that you want to look for, you are sending the hash of the keyword. Okay, upon reception, Bob, who is maintaining a local database with all the hashes of the keywords and the mapping with the file, he can basically trigger his database and look up on his database and find if there is the hash of coronavirus somewhere, and if there is, then he can find the files that contain this keyword, and basically he will return back the file to the user, right, who has initiated the search query. Upon reception, the user basically who has already access to the encryption and decryption keys he can decrypt the file, find out the entire contents of the underlying file, and do whatever she likes, like update the file or just read it or whatever. Right, good. So that's how it works, basically. So this is very simple. This is how SSC works in principle, right? There are several properties that we need to take care of when we build SSC schemes. For example, it's important to look at what forward and backward privacy is. For example, backward privacy means that when you delete a file, okay, Bob should not be able to understand the keywords that have been deleted and should not be able to do any kind of mapping between the keywords and the files, and he should not be able to, you know, connect any future queries or previous queries with the deleted files. Anyway, things that, you know, make the whole schemes more complete, I would say. But as I said earlier, I want you to get the main idea here, right? Good. So let's now move on to attribute-based encryption, and then we'll try to combine these two techniques together. So AB. So first of all, AB was introduced by Sahai and Waters. So this guy here is Sahai. The guy below is Waters. At that point, I think Waters was the PhD of Sahai at Stanford, I think. Anyway, it's a relatively recent approach and very active research area. So in traditional public key cryptography, a message is encrypted for a specific receiver using the receiver's public key, right? So if you want to send a message to Bob, you encrypt the message using Bob's public key, and then only Bob can decrypt that message because he's the only one who has access to the corresponding private key. That's basically how asymmetric encryption works. Now, ABE, attribute-based encryption, allows to encrypt messages with respect to subsets of attributes or policies defined over a set of attributes. The key points are that a user should only be able to decrypt a ciphertext if the attributes on his key matches the policy attached to the ciphertext. And keys are always issued by a trusted authority. So imagine that basically in ABE, each user has a unique key, which is based on a set of attributes. So, for example, my attributes could be, for example, date of birth 1982, name Antonis, surname Michalas, work at Tampere University, and so on and so forth. So, you know, usually those attributes are kind of personal, okay, and identify a certain person. And that's why, because we want these attributes to be reliable and true, they need to be issued by a trusted authority. Now, each user has a unique key that is based on a unique set of attributes. Now, every time that we encrypt the file, we attach a policy on the file. Now, if a user tries to decrypt that file at the later point, the decryption will work if and only if the attributes of that they exist on that user's key satisfy the policy that is attached on the corresponding ciphertext. If this doesn't work, then the decryption will fail. So this is the main idea. So let's see a bit more detail. So you have a lot of data stored in an encrypted database, right? A diverse set of users who will need access to different pieces of that data. So you've got a lot of data stored in an encrypted database and a diverse set of users who will need access to different pieces of data. So the problem here is who can access what data. So in AB, it is not the identity of the users that determines who should access the data, but attributes that can be common to many users. For example, age, country, company, gender, etc., etc. Okay, so with attribute-based encryption, we don't really care about the identity, but about the attributes, and the attributes and along with the policy will determine who is going to access which data. Now, we want to describe who can decrypt the data in terms of an access policy, and things can scale with the size of our description instead of scaling with the number of users, right? So if you basically make more complex policies, basically you increase the description of the policy. Okay, you make it a bit more complex, then you scale the complexity of the whole thing, but still this does not scale with the number of users that they will access the data. Okay, and this is very, very important to have in mind. Right, so let's get into a bit more details of how this strange thing ABE works. So in ABE, we've got an entity which we call a master authority, a master entity, right? That ninja here in your screen. So that master entity is a trusted entity, first of all, right? And it has a master secret keeper and a master public keeper. So MSK for master secret key, MPK for master public key. Now, keep in mind that only the master authority can generate keys for users. So the master authority, she's using MPK to do quite a lot of things, but also she's sending MPK to all of the users, right? So she's setting MPK with all users. So everyone here on your right, they get access to MPK, they know MPK. Apart from that, each user gets a list of attributes, okay? Usually through the master authority or anyway through another trusted authority that belongs to them. Anyway, has been defined in the architecture. Now, these attributes, as I mentioned earlier, they can be age, gender, work, town where they live, and so on and so forth. It can be basically anything, right? Now, the master authority, it needs to use his master secret key, MSK, along with the list of attributes for each user in order to generate users keys, right? So when that user Bob here, for example, sends a request to the master entity to generate his AB key, his AB secret key, the master authority will use will run a key generation algorithm that takes as input MSK, the master secret key, as well as Bob's unique attributes list, and this will output basically Bob's attribute-based secret key, that blue key, that will be sent to Bob, right? Now Alice here will do the same, and the other user will do the same, and so on and so forth. So at the end, each user will end up having a unique AB key, which is generated by the master authority using MSK and the unique list of attributes for each user, right? So each user ends up having their own unique keys. Good. So let's move now to the encryption and decryption process and see how this works. So we've got Bob, okay, that he wishes to encrypt a file, right? To encrypt the file, Bob will have to use MPK, right, the master public key. So we always encrypt our data in attribute-based encryption. We always encrypt our data by using the public key of the master authority. Good. Apart from these two, so the encryption algorithm will take as input the file that we wish to encrypt, MPK, as well as a policy, right? A policy that will basically define who can decrypt this file, right? So an example of a policy would be that, okay, the gender should be equal to female, and the user should work at TUNI, at Tampere University, or at VTT, and should be older than 31 years old, okay? Should be at least 32 years old, whatever. Good, so this is a policy. So policies in ABE, they usually use ands and ors, right? So the policy that Bob defined for his file says that the user should be a female, working at TUNI or VTT, and should be over 31 years old. Good. So this will generate basically an encrypted version of the file. Now, apart from that, let's see let's examine basically the attributes of those users that we have on the right side of our screen. So Alice here, she has the attribute gender equal to female, work at Tuni, and her age is 32. Excuse me. Then the other user here, she's again a female. She works at MIT and her age is 37. So let's see how this works now. So Bob basically encrypts his file, and this generates a ciphertext of his original file that is stored somewhere in the cloud, right? Now, at some later point, Alice, both users, they'll try to basically use their key to decrypt that file, right? And what will happen is that basically Alice will be able to decrypt the file successfully because her attributes satisfy the policy. You see, the gender is female, which she has that attribute, and works at Tuni, satisfies that attribute, and she's over 31 years old. While in the case of our friend here, her attributes that are on her key does not satisfy the policy because yes, she is a female, she is over 31 years old, but she works at MIT, not in Tuni or VTT. Therefore, her key will not work here. So she will not be able to decrypt that ciphertext with her key. While Alice, with her key, she managed to recover the file, right? So you see what I mean, that with different keys we can decrypt the same file, right? Which is amazing. I mean, yeah, it's good. Now, now the problem, what we have described here, two different cryptographic techniques, SSC and ABE. There is a problem here though. The problem with ABE is that is an asymmetric encryption scheme, which means that we cannot really use it to encrypt large volumes of data. It's really inefficient, right? So we cannot do it. Now, the problem with symmetric searchable encryption is how we can give access to our data, how to have a granular access control to our data, right? So how we can basically encrypt our data with SSC, but then how we can share that key with several users, and how we can later on, for example, revoke access from a user, or anyway give access to users based on certain policies, right? So one way to do this is to try to create a kind of a cryptographic protocol that would combine both SSC and ABE. That's what we are going to combine to describe here briefly, how we can create a cryptographic cloud storage based on ABE and SSC. So imagine that Alice, basically, she has her key, the symmetric key that she's using to symmetrically encrypt all of her data. So she generates a policy which basically says who can access her data, and she uses the master MPK, master's public key, to encrypt basically the actual key. So she's generating the symmetric key, and then she generates a policy and she encrypts that key with that policy, right? So she's encrypting that key with using ABE. Now that key, the encrypted version of her symmetric key, will be sent to the cloud, which will be stored locally. And then when we have another user that she wishes to access Alice's data, basically, that user will ask Alice's key from the cloud service, and the cloud service provider will return the key. That user will then basically use her ABE key to decrypt Alice's symmetric key, and if her attributes satisfy the policy, then basically she gets access to Alice's symmetric key, and then she can start using SSC directly by using Alice's secret key. So the nice idea here is that, you know, we realize that ABE cannot be used to encrypt a bunch of data. So basically we want to keep using SSC to encrypt our main data. So we will use ABE to encrypt the smallest possible information, which is just the key. And this will allow us to have a kind of granular access control over our symmetrically encrypted data. Okay, so we use SABE to encrypt our symmetric key, and then once we get access to that, we can use SSE for search queries and so on. An interesting paper is The Lord of the Shares, combining attribute-based encryption and searchable encryption for flexible data sharing. You can find it online. Yeah, and basically describes in a bit more detail exactly the system that you see on that slide. Now, another promising technique that many researchers keep working for years now, but lately has become even a very active research area, is what is called homomorphic encryption. We've got different versions of homomorphic encryption, semi-homomorphic encryption, fully homomorphic encryption. Doesn't matter. I just want to give you an example of what you can do with homomorphic encryption. So the word homomorphic has roots in Greek and loosely translated as same shape or same form. In relation to cryptography, the concept is that operations can be performed on encrypted data without sharing the secret key needed for decryption. Now, the idea of homomorphic encryption had been around for more than 30 years, but only recently we saw some great developments. So in 1999, Pascal Pelliet designed the first practical semi-homomorphic encryption scheme, while in 2009, Greg Gentry in IBM designed the first practical fully homomorphic encryption scheme. So let's see a simple example how homomorphic encryption works. So assume that Alice wishes to add two numbers, say A equals to 5 and B equals to 3, but she does not know how to add numbers. Quite strange, but yes, she doesn't. She thought of asking her friend Bob to do the addition, but lately they are not that good friends, and she cannot trust that he will do the operation correctly. Good. However, even though she does not know how to add numbers, she does know how to use encryption. So this is even more strange, but anyway. So what she can do is that basically she can encrypt the two numbers with her public key, pk of A. So she encrypts 5 with pk of A, and then 3 with pk of A, and she can send basically this to Bob, right? Now, Bob knows how to perform homomorphic encryption, and what he can do is that basically he can use the property of homomorphic encryption that allows him to add two numbers, right? So Bob basically can do the addition for Alice in the ciphertext, right? Directly in the ciphertext. So Bob basically will calculate EP, the encrypted version of 5 plus the encrypted version of 3, and will send back to Alice an encrypted version of 8 with Alice's public key. Upon reception, Alice basically that has access to her secret key will be able to decrypt this and find out the sum of 5 and 3. Now, homomorphic encryption allows you to perform operations directly on the ciphertext, which when decrypted would be the same as you would get if the operation performed on the plaintext. Now, imagine that these are pretty, I mean, this property is really important and can really solve issues like e-voting and privacy preserving e-voting. Imagine that if you want to collect, for example, the votes of in an e-voting scheme, the votes of all users, you want to make sure that all these votes will be remain private, right? So you can use homomorphic encryption to just calculate the sum of all votes without getting access to the individual votes. And there are many other scenarios where basically you can use homomorphic encryption to protect users' privacy. Now, the important thing to remember is that basically you can add up encrypted numbers without getting access to the individual values. Now, I believe that in the future we'll start seeing some applications of this kind of techniques. Because nowadays they start getting more efficient. Till recently they were quite inefficient to use, but there is a lot of progress lately. With this, basically, we end this lecture as well. This guy here, Seni Kamara, has done quite a remarkable work in the field of SSE. And yeah, you should look in one of his papers at least. Thanks a lot. See you later. Bye.